Hello, friends. Have you ever wondered if electrons really spin? This intriguing question dives deep into the heart of quantum mechanics, exploring the fundamental aspects of particle physics and the strange behavior of subatomic particles. From the quantum spin of electrons to the mysteries of quantum weirdness, this video will take you on an enlightening journey through the wonders of the quantum world. We'll demystify complex concepts, making them accessible to everyone, from beginners to advanced learners. Get ready to uncover the truth behind the quantum spin of electrons and discover the fascinating phenomena that govern our universe. Understanding the nature of electrons and their spin is one of the key challenges in quantum mechanics. Electrons are fundamental particles that form the building blocks of atoms, which in turn make up all the matter in the universe. Unlike larger objects that can be observed directly, electrons are incredibly small and behave in ways that are difficult to comprehend. One of the most puzzling aspects of their behavior is their spin. Spin is a fundamental property of electrons, much like charge and mass. However, unlike charge and mass, spin does not correspond to any visible motion. Instead, it is an intrinsic form of angular momentum that exists even when the electron is at rest. This concept is counterintuitive because in our everyday experience we associate spin with objects rotating around an axis. In the quantum world, however, spin is a purely quantum mechanical property that does not have a classical analog. To understand electron spin, we need to delve into the principles of quantum mechanics. Quantum mechanics is the branch of physics that deals with the behavior of particles at the atomic and subatomic levels. One of the core principles of quantum mechanics is the wave-particle duality, which states that particles such as electrons exhibit both wave-like and particle-like properties. This duality is crucial for understanding electron spin. In the early 20th century, physicists were puzzled by the behavior of electrons in atoms. They discovered that electrons could not be fully described by classical physics, which led to the development of quantum mechanics. One of the key discoveries was that electrons have a property called spin, which can take on values of either +1/2 or 1/2. This discovery was made through experiments that measured the magnetic properties of electrons. Electron spin is closely related to magnetism. When electrons move, they generate a magnetic field. This magnetic field can be influenced by the electron's spin. In fact, the spin of an electron contributes to the overall magnetic moment of an atom. This is why materials with unpaired electrons, such as iron, exhibit strong magnetic properties. The concept of spin is also crucial for understanding the Pauli exclusion principle. This principle states that no two electrons in an atom can have the same set of quantum numbers. In other words, each electron in an atom must occupy a unique quantum state. The inclusion of spin in the quantum state of an electron helps explain the structure of the periodic table and the behavior of atoms in chemical reactions. One of the most fascinating aspects of electron spin is its role in quantum entanglement. Quantum entanglement is a phenomenon where particles become interconnected in such a way that the state of one particle cannot be described independently of the state of another. When two electrons are entangled, the spin of one electron is directly related to the spin of the other, no matter how far apart they are. This phenomenon has been experimentally verified and has profound implications for our understanding of the universe. The study of electron spin has led to numerous technological advancements. For example, the field of spintronics exploits the spin of electrons to develop new types of electronic devices. Unlike traditional electronics, which rely on the charge of electrons, spintronics uses the spin to store and manipulate information. This has the potential to create faster, more efficient, and more secure forms of data storage and processing. Scientists use several techniques to measure and manipulate electron spin, starting with the Stern-Gerlach experiment. In this experiment, a beam of electrons passes through a non-uniform magnetic field, which interacts with the electrons' magnetic moments caused by their spin. This causes the beam to split into two separate paths, corresponding to the spin-up and spin-down states. By detecting which path the electrons take, scientists can measure their spin. Electron spin resonance, ESR, also known as electron paramagnetic resonance, EPR, is another important technique. In ESR, a sample containing unpaired electrons is placed in a strong magnetic field and exposed to microwave radiation. The magnetic field causes the electron spins to split into different energy levels. When the energy of the microwaves matches the energy difference between these levels, the electrons absorb the radiation and transition between spin states. By measuring this absorption, scientists can determine the spin states and other properties of the electrons. Nuclear magnetic resonance, NMR, is typically used to study atomic nuclei, but can also provide information about electron spin. In NMR, a sample is placed in a magnetic field and exposed to radio frequency radiation. The magnetic field causes the nuclear spins to align in different energy levels, and the surrounding electrons create small local magnetic fields that influence these nuclear spins. By analyzing the NMR signals, scientists can infer details about the electron spin environment. Scanning tunneling microscopy, STM, allows scientists to image and manipulate individual atoms and molecules on surfaces. A sharp metal tip is brought close to a surface and a voltage is applied between the tip and the surface. Electrons tunnel between the tip and the surface, creating a tunneling current that is sensitive to the spin state of the electrons. By precisely controlling the position and voltage of the tip, scientists can manipulate the spin states of individual electrons and study their effects on various materials. Optical techniques like Faraday rotation and Kerr rotation involve passing polarized light through a material with unpaired electrons or reflecting it off a surface. The interaction between the light and the electron spins causes the polarization of the light to rotate. By measuring this rotation angle, scientists can gain information about the spin states of the electrons in the material. Magnetic resonance imaging, MRI, widely used in medicine, also has roots in electron spin measurements. MRI uses strong magnetic fields and radio frequency pulses to create detailed images of the inside of the human body. The principles behind MRI are similar to those of NMR, and understanding electron spin is crucial for interpreting MRI data accurately. To manipulate electron spin, scientists often use magnetic fields and electrical currents. Magnetic fields can align or flip the spin of electrons, while electrical currents can create spin-polarized currents where most electrons have the same spin orientation. These spin-polarized currents are essential in spintronics, where the spin of electrons is used to store and process information. Quantum dots are tiny semiconductor particles that confine electrons in all three spatial dimensions, creating discrete energy levels. By applying electric and magnetic fields to quantum dots, scientists can precisely control the spin states of the electrons within them. This control makes quantum dots a promising platform for developing quantum computers and other advanced technologies. Laser techniques are also used to control electron spin. Circularly polarized light, where the electric field of the light rotates in a circular motion, can selectively excite electrons with a particular spin state. By adjusting the polarization of the light, scientists can control the spin states of electrons in a material, allowing for detailed studies of spin dynamics and interactions. Overall, the measurement and manipulation of electron spin are fundamental aspects of modern physics and technology. These techniques enable scientists to uncover new insights into the behavior of electrons and the nature of quantum mechanics, paving the way for future technological innovations. Quantum mechanics, with its strange and counterintuitive principles, raises many philosophical questions that challenge our understanding of reality. The concept of electron spin, in particular, brings several deep philosophical issues to the forefront. One of the most intriguing questions is the nature of reality itself. In classical physics, objects have well-defined properties, such as position and momentum. However, in quantum mechanics, particles like electrons do not have definite properties until they are measured. This leads to the question, what is the nature of reality before measurement? Is there an objective reality independent of our observations? Or do our measurements somehow bring reality into existence? Another philosophical question concerns the nature of determinism. Classical physics operates under the principle of determinism, where the future state of a system can be predicted with certainty if the current state is known. In contrast, quantum mechanics is inherently probabilistic. The outcomes of measurements are not deterministic but are described by probabilities. This raises the question of whether the universe is fundamentally random. If so, what does this mean for the concept of free will and the predictability of future events? The concept of superposition, where particles can exist in multiple states simultaneously, also poses philosophical challenges. Entanglement, another cornerstone of quantum mechanics, suggests that particles can become interconnected in such a way that the state of one particle instantaneously affects the state of another, regardless of the distance between them. This phenomenon, famously described by Einstein as spooky action at a distance, challenges our understanding of causality and locality. It raises the question of how information can be transmitted instantaneously, and whether there is a deeper level of reality that we do not yet understand. The role of the observer in quantum mechanics is another profound philosophical issue. The interpretation of quantum mechanics itself is a major philosophical debate. There are several interpretations, each with its own implications for our understanding of reality. The Copenhagen interpretation, for instance, suggests that the wave function representing a quantum system collapses to a definite state upon measurement. In contrast, the many worlds interpretation proposes that all possible outcomes of a quantum measurement actually occur, each in a separate parallel universe. The philosophical questions raised by quantum mechanics and electron spin are profound and far-reaching. They challenge our traditional concepts of reality, determinism, causality, and the role of the observer. In the future, leveraging electron spin could revolutionize various fields of technology. One exciting area is quantum computing. Unlike classical computers, which use bits to process information in binary form, 0s and 1s, quantum computers use qubits. Qubits can exist in multiple states simultaneously, thanks to the principles of superposition and entanglement. Electron spin can be used to create qubits, which can perform complex calculations much faster than classical computers. This could lead to breakthroughs in cryptography, optimization problems, and simulations of molecular structures, which are crucial for drug discovery and materials science. Spintronics is another promising field that could benefit from electron spin. Traditional electronics rely on the charge of electrons to transmit and store information. Spintronics, on the other hand, uses the spin of electrons, which can increase the speed and efficiency of electronic devices. Spintronic devices can have lower power consumption and generate less heat compared to conventional electronics. This could lead to more powerful and energy-efficient computers, smartphones, and other digital devices. Data storage is another area where electron spin could have a significant impact. Current data storage technologies, such as hard drives and solid-state drives, rely on the magnetic properties of materials. By manipulating electron spin, scientists can develop new types of memory devices that are faster, more durable, and capable of storing more data. For example, magnetic random access memory, MRAM, uses electron spin to store data and has the potential to replace traditional RAM and flash memory. Medical technology could also see advancements through the use of electron spin. Techniques like magnetic resonance imaging, MRI, already rely on principles related to spin. Future technologies might use spin-based sensors to detect diseases at an earlier stage, providing more accurate diagnoses and better treatment options. Additionally, understanding and controlling electron spin could lead to new methods of targeting and destroying cancer cells, improving the effectiveness of treatments. Communication technologies could be transformed by electron spin as well. Quantum communication uses the principles of quantum mechanics, including entanglement, to create secure communication channels that are immune to eavesdropping. By leveraging electron spin, scientists can develop quantum networks that enable secure and instant communication over long distances. This could revolutionize how information is transmitted and ensure the privacy and security of data. In the field of energy, electron spin could lead to more efficient ways of generating and storing power. Spin-based materials and devices could improve the efficiency of solar cells and batteries, reducing our reliance on fossil fuels and promoting sustainable energy sources. For example, spintronic materials could be used to develop next-generation solar panels that convert sunlight into electricity more efficiently. The exploration of space might also benefit from advances in electron spin technologies. Quantum sensors that use electron spin could provide more accurate measurements of gravitational fields, magnetic fields, and other physical phenomena. This could enhance our ability to navigate and explore space, leading to new discoveries about our universe. The future of technology leveraging electron spin is incredibly promising. From quantum computing and spintronics to medical advancements and secure communication, the potential applications are vast and transformative. As scientists continue to unravel the mysteries of electron spin and develop new ways to manipulate it, we can expect to see groundbreaking innovations that will shape the future of technology and improve our lives in countless ways. Thank you for joining us on this journey through electron spin. Please like, comment, and share the video, and please do not forget to subscribe for more videos.